Alright, so ready to start chapter 8 here. So we have chapter 8 to do, and then chapter 9, and then we're finished with the class, right? So chapter 8 is hypothesis testing for population proportions. So the main topic here for chapter 8 is being able to conduct what we call hypothesis testing involving 1 and 2 population proportions, right? So hypothesis testing is considered the heart of statistics, and often we use this when comparing two things to see which is better, right? So this is a more like scientific way to see which thing is better, right? So we're gonna go through this. So section 8.1 is titled the essential ingredients of hypothesis testing. So we're going to be able to write a null and alternative hypothesis for a test involving a population proportion, and also be able to compute and interpret a test statistic and p-value, right? So this will help set the stage for us to do hypothesis testing. So hypothesis testing here is a procedure that enables us to choose between two claims when we have variability in our measurements, right? So the two claims we call the null hypothesis and the alternative hypothesis, right? So in general, the textbook recommends or suggests that there are 4 steps involved with hypothesis testing. The first step is to hypothesize. So you're going to state a hypothesis, which is a claim that will be weighed against a neutral skeptical claim, right? So step 2 is to prepare. You need to determine how you'll use data to make your decision and make sure you have enough data to minimize the probability of making mistakes. The third step is that you will collect data and compare them to your expectation. And then lastly, step 4, interpret. So state your conclusion and answer the question, do you believe the claim, or do you find that the claim doesn't have enough evidence to back it up, right? So here is an introductory example to get us started. So imagine a coin is spun on a flat surface. We are hypothesizing it is more likely to come up heads because that side of the coin bulges out slightly compared to the tail side, right? So that's what our claim is. So we spin the coin 20 times and it comes up heads all 20 times. If it was equally likely that the coin stopped on heads or tails after spinning, it would be very unusual to find 20 heads and 20 spins of a coin, right? So, you know, if it were fair, we would expect it to be 10 or close to 10, right? 20 out of 20 seems very unlikely. So this is so unusual that you would conclude that your hypothesis that your coin is more likely to come up heads when spinning is correct, right? So we have this instance where it's very unlikely, so they would make one believe that it is more likely that heads would come up, right? So number 1, we did state hypothesis that the coin is more likely to come up heads and test this against a neutral hypothesis that the coin is fair, right? Step 2, we decided you would use the proportion of heads in 20 spins of the coin to test your hypothesis, and we collected data. 20 spins result in 20 heads and compare them to my expectation. So if the coin was more likely to land on heads, you would expect about 50% of the spins, or about 10 spins, right, to result in heads. However, we got a result of 20 heads, which is much greater than you expected, right? Then step 4, so because it would be so unlikely to get 20 heads and 20 spins if the coin were equally likely to land on heads or tails when you spun, then we can conclude that the coin is more likely to land on heads when spun, right? So there's kind of a guiding example to help us think through this. So as I mentioned before, we're going to have 2 hypotheses, right? So these are a pair of hypotheses. We're going to have what's called a null hypothesis, and you can see how it's shown there. The null hypothesis is shown as x naught. And it's important to note that the null hypothesis is going to be my neutral, my status quo, my skeptical statement about a population parameter, right? And since this is such, it will always contain equals, right? So the hypothesis, or the alternate hypothesis, is shown as H sub A, right? Or, whoops, sorry, I didn't mean to skip around there, right? Sorry about that. So this is also the alternate hypothesis. Some textbooks also show this as H, whoops, that's not a very good H, as H sub 1, right? So H sub 1 is another way to show the alternate hypothesis, right? So some texts might use H sub 1, our text uses H sub A, right? So the research hypothesis is the alternate hypothesis. That's the statement about a population parameter we intend to demonstrate is true, right? So this is always going to contain one of these symbols, right? Less than, equal than, or not equal to, right? So if we use an equal sign, right? Some words that you might see like are maybe is or has stayed the same. Right? Something like that. Right? So some words you might use the not equal sign. Right? You might see something like is different from, has changed from, differs from, right? So is different from, has changed from, or maybe differs from. And to use greater than, some synonyms that you might see is below, is smaller than, or has decreased. Right? So that might help you just know some English words for the symbols, right? So these are my symbol. These are synonyms, right? And this is an important note here also, right? Hypotheses are always about the population parameters, right? They're never about sample statistics, right? So, for example, if we're talking about means, we would use mu, right? That's the population parameter. Or if we're talking about population proportions, right? We use P, right? Alright, so the next slide, we look more at the null hypothesis. So the null hypothesis always gets the benefit of the doubt throughout the hypothesis testing procedure. So we only reject the null hypothesis if the observed outcome is extremely unusual if the null hypothesis were true, right? So in other words, this is analogous to assume that a defendant in a jury trial is innocent unless proven guilty beyond a reasonable doubt, right? So comparing that to our justice system is similar and can help you remember that, right? So here's another example of global warming. So a 2014 Pew poll found that 61% of Americans believed in global warming. A researcher believes this rate has declined. State the null and alternate hypothesis in words and in symbols, right? So to put this in symbols and words, we would say the following, right? So remember, the null hypothesis always has equals, right? So the null hypothesis P equals 0.61. So in words, that means the same proportion of Americans believe in global warming as in the past, right? And then the alternate hypothesis is P less than 0.61. So the proportion of Americans who believe in global warming has decreased, right? So sometimes we have what we call one-sided or two-sided hypothesis testing. So the sign in the alternate hypothesis tells us if it's one-sided or two-sided, right? So it's two-sided if my alternate hypothesis is not equal to, right? It's one-sided, or what we call a left-tail test, if in my alternate hypothesis P is less than P naught, right? And then it's one-sided, or right-tail test, if P is greater than P naught, right? So this is what we call right-tail test. Right-tail test. This is a left-tail test, and this is a two-tail test, right? So here's example. So during the previous fiscal year, 30% of a retailer's sales were due to online sales. In an effort to increase this percentage of the retailer's purchase ads on social media sites, the retailer gathers data on types of sales on a sample of 20 days during the current fiscal year. Has there been a change in online sales? Right? So we want to be able to write the null and alternate hypothesis for the retailer. We want to identify, is it one-sided or two-sided hypothesis, and what other hypothesis could the retailer have posed, right? So, for my my null hypothesis, we have P equals 0.3, right? In my alternate hypothesis, we would say P is not equal to 0.3, right? So this is a two-sided hypothesis, right? So when I use not equals, that's double two-sided, right? So the retailer could have asked also, have sales increased, right? So if we ask this question, then my null hypothesis is the same, right? Notice my null hypothesis is the same no matter what, right? So always equals. But if we would have asked, have sales increased, then my alternate hypothesis would be P greater than 0.3, right? So increase referring to that it's more than 0.3. So this is what we call a one-sided or right-tail test. So if the retailer had asked, have sales decreased, right, then my null hypothesis is still the same. My alternate hypothesis is P is less than 0.3, right? And this would be a left-tail test, right? One-sided. So another thing that we need to discuss is called a significant level. So the significant level is the probability of making the mistake of rejecting the null hypothesis when in fact the null hypothesis is true, right? So the symbol we use is alpha, right, which is here. So this is the symbol we use for the significance level. So for most applications, we use a significance level of 0.05, right? This is the most widely accepted significance level, right? But we could use 0.01 or 0.10, right? Or also sometimes used. So this 0.05 number is just a number that lots of people use and agree upon, right? It's nothing necessarily special. So sometimes we have to change it depending on what we know about the population, right? So the alpha level will be given to you, right? And we also call alpha, this is what we recall the type 1 error. Type 1 error, right? So if you imagine this this chart, right? So let me say the null hypothesis here, let's say it's true, and here it's false, right? And then over here, I'll put that we failed to reject, and here that we reject, right? So if my null hypothesis is true, and I failed to reject it, which means I don't reject it, that's a good thing, right? So we can put a smiley face, right? So it's true, and I'm accepting it, right? So that's a good thing, right? We accepted something true. We didn't lie, in a sense, right? But if my null hypothesis is true, and I reject it, that's not good, right? We call this type 1 error, so or alpha, or type 1 error. If my null hypothesis is false and I reject it, then that's fine, right? That's correct. So we get a smiley face, right? But if my null hypothesis is false and I fail to reject it, which means I'm accepting it, that's bad, right? We call this type 2 error, or the symbol is beta, right? So Greek letter beta, right? So this is what we're talking about, right? So alpha is the probability that my null hypothesis is true, but I reject it, right? So it's making a mistake of rejecting the null hypothesis when in fact the null hypothesis is true, right? So beta would be the probability that my null hypothesis is false and I fail to reject it, right? All right, so the next slide is my test statistic. So the test statistic compares our observed outcome with the outcome we would get if the null hypothesis is true, right? So when the test statistic is far away from the value, we would expect that if the null hypothesis is true, we reject the null hypothesis and conclude the evidence supports the alternate hypothesis. So notice the wording here. We say that evidence supports the alternate hypothesis. So we use language like this when we interpret after doing a hypothesis testing. We never say that this is definitely true, right? We say that we have statistical evidence to support this, right? So that's an important thing. We don't know if it's true or false. We just say, based on our statistical evidence, this is what we believe to be true, right? So my test statistic that we can use, right, is z, right? If we have a normal distribution, right, as we've been doing before. So the test statistic always has this structure, right? Z equals my observed value minus my null value divided by my standard error, right? So if we have a test statistic, we can say Z equals p hat minus p0 divided by standard error, which here is standard error, right? And we're told here what p hat and p sub 0 is, right? So p hat is the sample proportion, right, from our data, and p naught is the proportion found in your null hypothesis, right? So here's an example of global warming. So in 2001, the Gallup poll reported that 12% of Americans were cool skeptics who reported worrying a little or not at all about global warming. In 2014, 25% of those reporting to a Gallup poll classified themselves as cool skeptics. Assume that the sample size for the 2014 poll was 500. Can we conclude that the percentage of Americans who identify themselves as cool skeptics has increased since 2001? Calculate the test statistic and explain the value in context, right? So if we go to the next slide, we can calculate that, right? So we need to identify what my null and alternate hypothesis are, right? So these are such, right? We would have p equals 0.12, and here we were trying to see if it had increased, right? So we would say p is greater than 0.12. So plugging those values in for my test statistic, I get a test statistic of 8.95. So this observed value of the test statistic is 8.95. This means that while the null hypothesis claims a proportion of 0.12, the observed proportion was much higher, right? 8.95 standard error is higher, right? Which is really high, right? Than what the null hypothesis claims. So the null hypothesis tells us what to expect when we look at our data. If we see something unexpected, that is, when we are surprised, then we should doubt the null hypothesis. So if we are really surprised, we should reject it altogether. So this p-value gives us a way to numerically measure this, right? Measure our surprise. So how unusual is this? So it reports the probability that if the null hypothesis is true, our test statistic will have a value as extreme or as more extreme than the value we actually observe, right? So small p-values close to 0 mean we are really surprised. Large p-values closer to 1 mean we are not surprised at all, right? So that's how we can interpret those. So if we get a p-value that is less than our significant level, right? So if p is less than our significant level, which we denote by alpha, right? Then our p-value is considered small. We are really surprised, so we reject. So if p is less than alpha, we reject. We reject the null hypothesis, right? And we accept the alternate hypothesis, right? But if we get a p-value greater than alpha, then we fail to reject. fail to reject. Right? In other words, we say that there's not enough statistical evidence to reject the null hypothesis, right? So, or the null hypothesis. So we accept null hypothesis to be true, right? We don't have statistical evidence to believe otherwise. That is not true. Right? So here's the last slide that I have. So in our example on global warming, we had test statistic of 8.95. So if we use StatCrunch, we conclude the probability of getting a test statistic at least as extreme as 8.95. Right? So my z value is 8.95. Right? So in other words, I'm trying to find the probability, right? What's the probability that that z is bigger than 8.95, right? So using so here they use StatCrunch to calculate this, right? But I've already shown you how to use your graphing calculator or R to calculate this, right? So if I want to find the probability that z is greater than 8.95, right? Here this comes out to be approximately 0, right? With our StatCrunch. So since 0 is less than alpha of 0.05, then we're going to reject our null hypothesis. In fact, it gives us strong evidence too, right? So we conclude that the percentage of Americans who identify themselves as cool skeptics has increased, right? So my alternate hypothesis was that it increased, right? So we accept this, right? So we accept this. So, but again, we accept it, but we don't say it's definitely true, right? We say that, you know, there is strong statistical evidence to support the idea that the cool skeptics has increased since 2001, right? All right, so we're going to be doing a lot more with hypothesis testing, but I wanted this to give you a good intro about what we're doing and set the stage for some other sections, right?